We have misunderstood the universe. Those are the words of Nobel Prize-winning physicist Adam Rees, a man who has spent his career measuring how fast the cosmos is flying apart, and who is now looking at data that contradicts our existing math. Modern cosmology rests on a framework known as the Standard Model. It consists of a specific set of equations that has accurately predicted the behavior of the universe from the first fraction of a second after the Big Bang. The current tension starts with a single metric called the Hubble constant, which measures the rate at which the universe is expanding today. When astronomer Edwin Hubble first calculated this rate in the 1920s, his results suggested the universe was younger than the Earth itself. Astronomers debated the true expansion rate for decades, but by the early 2000s, the field reached a consensus. The universe was expanding at roughly 70 kilometers per second per megaparsec. As our observational tools became sharper, a new gap emerged. Two independent, highly precise methods for measuring this expansion are returning answers that are 9% apart. This discrepancy implies the observable universe might be over 1 billion years younger than we previously calculated. This map shows the cosmic microwave background, the faint radiation left over from the early universe. By taking these initial conditions and running the Standard Model equations forward 14 billion years, physicists arrive at a predicted expansion rate of 67. Adam Rees and his team measure the present universe directly to check that prediction. They use the cosmic distance ladder to track the brightness of nearby pulsating stars and exploding supernovas. When they calculate the expansion rate based on these direct observations, they get 73. Initially, scientists suspected a mechanical error with the Hubble Space Telescope. One theory was stellar crowding, the idea that thick dust in young galaxies was blending the light of nearby stars, which would artificially inflate the expansion measurements. Astronomers pointed the James Webb Space Telescope at those same stars. Its massive gold-plated mirror and infrared cameras were designed to cut through cosmic dust and provide a crystal-clear reading. Webb's sharp vision confirmed the Hubble numbers exactly. The stars looked the same, the distances held, the expansion rate stayed at 73. These precise measurements suggest that our current model of reality is missing a significant piece of physics. Complicating the debate, astronomer Wendy Friedman developed a different way to measure the local universe. Instead of using pulsating stars, her team uses red giants, which exist in less crowded, less dusty regions of galaxies. When Friedman ran her analysis through Webb, her results landed at 70. This value sits in a middle ground. It fails to confirm the Standard Model's 67, but it also falls short of the 73 measured by Rees. Nobel laureate Saul Perlmutter noted that the star-based measurements are yielding different answers among themselves, even before being compared to data from the early universe. This indicates that the foundational tools used for a century to map nearby space may contain unresolved issues that cannot be fixed by simply using a better telescope. While astronomers debate expansion, Webb has uncovered a separate anomaly in deep space. The telescope found massive, fully formed galaxies existing only 500 million years after the Big Bang. This chart compares star formation limits. The Standard Model says a young galaxy should only convert about 10% of its surrounding gas into stars. Webb's data showed early galaxies apparently converting every scrap of raw material into stars, with zero waste. Researchers found that some of these massive readings were optical illusions. Many of these early objects host supermassive black holes. As these black holes devour gas, the friction creates intense light that mimics the brightness of billions of extra stars. Even after filtering out these black hole illusions, the data shows twice as many massive galaxies as permitted by current physics. Webb has even spotted a highly mature spiral galaxy, nicknamed the Big Wheel, existing incredibly early in the cosmic timeline. Orderly spiral structures require billions of years to develop. Discovering a galaxy this young indicates that the early universe was assembling complex structures far faster than our current models allow. The shapes of these infant galaxies are also unusual. Webb observed that many young galaxies are strikingly elongated, resembling cosmic cigars. This diagram compares theoretical dark matter structures. The standard cold dark matter model predicts galaxies cluster in neat, spherical shapes. These elongated galaxies actually match predictions from alternative models, like warm or wave dark matter. This shape anomaly pairs with a secondary problem known as the S8 tension. When astronomers measure the distribution of matter across space, they find the universe is less clumpy than the standard model predicts. Cold dark matter serves as the structural framework for the standard model. These structural anomalies indicate that the cosmic distribution of matter deviates from our existing predictions. Despite these fractures, the standard model accurately accounts for the cosmic microwave background and the exact abundances of hydrogen and helium in the universe. Cosmologists are now exploring specific revisions to the model, such as early dark energy, to reconcile these new observations with what we already know. This timeline illustrates a brief pulse of expansion. If the universe received an extra kick of energy shortly after the Big Bang, it would shift the older predictions upward to match Webb's modern 73 measurement, without breaking the rest of the equations. Because no one has detected this early energy, physics is entering an era of theoretical exploration to explain the 14 billion-year gap between the beginning of the universe and today. Physics has navigated similar tensions before. In the 1990s, measurements suggesting the universe was younger than its oldest stars directly led to the discovery of dark energy. Cosmologists view these current anomalies with productive excitement. Finding a result that contradicts a century of theory allows them to identify exactly where the current model reaches its limits. We are currently building the tools to map these blind spots. Upcoming missions like NASA's Roman Space Telescope and the European Space Agency's Euclid are being deployed to study the geometry of space at an unprecedented scale. These observational cracks represent the frontier of human knowledge. The next model of the cosmos will likely describe a reality even more complex than the one we are currently tracking.